Hey, Algebra 2. We are in Chapter 2, Lesson 2. We already did Part 1, and you may have experienced some dead time or no talking for a little while. Well, that's because I wasn't done yet, and apparently the video kept sort of moving ahead, but I wasn't ready for that. So, let's go ahead and finish this lesson. First of all, end behavior. This is a little bit hard, but you guys can get it. I know you can. So the end behavior of a function's graph is the behavior of the graph as x approaches positive infinity or negative infinity. So x, if you remember, I have an axis, an x and a y axis. So this is the x-axis. When x approaches positive infinity, that's that way. When x approaches negative infinity, that's this way, right? So that's what we're doing when we talk about x approaching positive infinity and negative infinity. So moving on. For the graph of a polynomial function, the end behavior is determined by the function's degree and the sign of its leading coefficient. So what is happening to the y, the up-down, as x approaches this and x approaches that? So let's look at it. When we have an odd degree, that means we are x cubed or x to the fifth or x, right? When our leading coefficient is positive, we have like a 4x. It doesn't matter. It's just not negative or a 1. It just has to be positive, the leading coefficient. So as x, right here, as x approaches positive infinity, our function, our graph, our curve is going up to positive infinity. Okay, as x approaches positive infinity, the function or the curve is going to positive infinity. As x approaches negative infinity, the curve or the function is going to negative infinity. So that's for an odd. When it's odd and negative leading coefficient, instead of a positive one, it's a negative one. When as x approaches negative infinity, the function or the curve approaches positive infinity. So as x is going in this direction, our curve is going up. As x is approaching positive infinity, our curve is going down to negative infinity. Okay, odd is always going to be up and down. Whether it's a third degree, a fifth degree, or even a first degree, which is a line, it's always going to be up and down. Or up and down. Okay? It's this way if it's a positive leading coefficient, and that way if it's negative. Alright, now let's go to even. Okay, we're even, like x squared, x to the fourth, x to the eighth, etc. when my leading coefficient is positive. Okay, when x is in the negative direction, my curve is going up. When x is in the positive direction, my curve is going up. Same thing, even, but negative leading coefficient, it reflects over the x-axis. So that's negative, that's negative, that's negative, that's negative. So this is reflect, opens down. Okay, in chapter 1, you guys learned this. X squared plus x plus 1. Okay? When that's positively leading coefficient, it opens up. Okay? Negative. Opens, oh my goodness, sorry, opens down. Alright, so let's try one. What is true about the degree and leading coefficient of the polynomial function whose graph is shown? Well, let's look at it. X is in the negative direction, your function is negative. X is in the positive direction, your function is negative. So, when they're both on the same side, we are even. And it's opening down, so it's a negative leading coefficient. So we are even, and the leading coefficient is negative. That means we're D. All right, so let's practice a few. First of all, synthetic substitution to evaluate the polynomial. I need to write all of my coefficients. So 5, 3, -1, and 7. And this would be a 2. I bring the 5 down, I multiply and add, I multiply and add, and I multiply and add. So I got 43. Hold on. Apparently I can't add. Not sure what I was thinking. Whew. Alright, we're already written in standard form. I've got a -2, -1, a 0x squared, don't forget your placeholders, 4x, and -5. We're plugging in a -1. Bring the -2 down, and we multiply. -1 times -2 is +2, and we add. Multiply and add, multiply and add, and multiply and add. -10 it is. Describe the degree and leading coefficient of the polynomial whose graph is shown. Well, I know when it's like this or like this, it's definitely odd. I need to sometimes check the chart, but I know if this is x's in the negative and this is positive, x is positive and this is negative, it is a negative leading coefficient. Oh, now we get to graph them. I think this is the hardest part, but we can use our graphing calculators to help us out. So to graph a polynomial function, first plot points to determine the shape of the graph's middle portion. Okay, then use what you know about end behavior to sketch the ends of the graph. Okay, so plotting points is somewhat hard, but we can do it. For this first one, I know that it's odd and it's negative, so it's going to look like this. I'm not sure where it looks like that on the graph, but we can figure it out. So let's plot some points. I'm making a t-table. Yes, old school. Now we can put this into our calculator. Remember, we learned how to store x's, and if you don't remember, please ask me in class. I would love to help you. So if I go ahead and store and type in the function just as I see it, I've stored -3 for x, so my y is going to be 24. If I store -2 and I do the same problem, I get a 3. -1, 0. Notice 0 is -3. If we put in 0 for x, it knocks them all out. Plug in a 1, a 2. Cool. So if we were to plot this, we don't have to plot all the points. We know the general behavior. I've got negative in third power, so it looks like that. When x is 0, y is -3. It's a great point to plot. This is another good one to plot. When x is 1, y is 0. So that's going to be right here. Let's go ahead and plot any other points we've got. Let's see, x is -1, y is -4, so it's down here. -2, 3. So I think we have a general idea. Let's see, we did +1, how about +2 with -1 right there. So we can make our general curve. Cool? Okay, let's try another one. This is a 4th degree positive leading coefficient. So t-table, same thing. I'm going -3, -2, -1, 0. And I can store, -3 for x, and just type in the equation as I see it, and it's super easy to spit out the values. Ooh, another thing you can do is put this into y equals. And look at your table for all of your x values and y values. I can show you how to do this tomorrow too. Just ask. Cool? It's much easier. Not much easier, just less work. And I'm all about less work if you understand what's going on, right? Okay, let's graph it. So right here at x equals 0, y equals 4. Cool. And then at x equals 1, y equals 0. Those are good ones to know. X equals 2, y equals -4. Notice I'm not plotting them all. Like the 22 and the 76 aren't getting plotted, right? What else? I can do -1, 2. -1, 2. Cool. Now this is a y to the 4th power. You can always graph it in your calculator to get an idea too, but it's going to look something like this. It's a little harder to do. Cool. All right, solve a multi-step problem. The energy E in foot-pounds in each square foot of a wave is given by the model. E equals that, where S is the wind speed in knots. Graph the model. Use the graph to estimate the wind speed needed to generate a wave within 1,000 foot-pounds of energy per square foot. Yikes. So our t-table is going to be a little bit different this time. Instead of x and y, we're doing s and e. Let's see. We're just going to do a few points. I know it'd be hard to figure out what points to do if I were sitting in your chair. So we're just going to learn from experience. I'm going to plug those in and check my answer. So when I plug in 0 for s, I get 0. 10 to the 4th power is a big number. Multiply that. 20 to the 4th power. $30 to the 4th power. 40 to the 4th power. Okay, I need to check that out and remember it as I graph what's going on. This is a real world problem again, so I really just want the first quadrant. And I know that doesn't make it easy, so sorry, this is going to be the s-axis and the e-axis. So that would be at 0, 10, 20, 30. These are the points I plugged in. So at 10, we're pretty small still. At 20, we're up at about a little less than 500. $1,000, $2,000, $3,000. So at 20, we're about halfway. At 30, we were at 2,394, so maybe around there-ish. And then at 40, we're at 7,000, which is way high. I'm not graphing that one. So that's where we are, and it says to estimate, use the graph to estimate the wind speed needed to generate a wave at 1,000. Okay, if I were using something to estimate, I would definitely use graph paper, not just my willy-nilly little graphs. So that looks to be less than 25, so let's guess S is about 24 when E is 1,000. So the wind speed needed to generate the wave is about 24 knots. Okay, oops. Awesome. Let's guided practice. So it's just a little bit of extra practice. I've got a fourth power positive. So xy, -3, -2, -1. I'm going to use the table this time because I'm getting smarter. So I just put it in my y equals, and I'm looking at the table. It also allows me to get a quick look at the graph, just to get an idea of what it looks like. So definitely opens up. Looks like at 0 we're at -3. At -1 we're at +4. And at +1 we're at +4. So our graph looks sort of like a parabola. Third degree leading coefficient. I'm going to plug that into my y equals really quick and check out the table to get my values. So 2x to the cube, to the third power, plus x squared, plus x minus 1. Check out my table. So -3, -2, 1, 0, 1, 2, 3. -49, -15, let's just check out the graph, what it looks like. Okay, if we're positive, that means that we're going to look a little bit like this somehow. We cross the y-axis at -1. And then over at 1, we're up 1, 2, 3. At -1, we're down 1, 2, 3. So that really gives us a good look of what we have. So starting from down there, point of inflection, and going up. Not bad.